Hello everyone, let's continue the discussion on the valence bond theory. And as we discussed in the previous vodcast, the valence bond theory is actually went a step further than the Vesper theory. And remember the process. You go from the Lewis structure to the electron group geometry, then to the molecular geometry, then to the bond angle, and then talking about the molecular polarity. All those are is based on the Vesper theory. And now we are looking at the details, how those bonds are formed. This is combined bonding with geometry, and the valence bond theory also addresses the equality of bonds in a molecule as far as length and energy are concerned. And this is looking into the detail how those single bond, double bond, or triple bonds are formed, and how those valence electrons are shared between the two atoms that are forming the covalent bonds. Here's the brief rundown for the valence bond theory. Explains how bonding actually those bonds are formed. And remember, just reiterate the principle of the valence bond theory is we first have to have atomic orbitals overlapping. And remember Schrodinger's quantum mechanical model of atoms, and the electrons surrounding the nucleus are situated on those three-dimensional regions. We call it orbitals, So you have to have the overlapping of the atomic orbitals before you can share the valence electrons. And as we're going to see later on, as new set of hybridized orbitals may form out of necessary, and lone pairs of electrons are localized on one central atom, or one atom that will be on a central atom. So let's take a look at the recall. We have looked with the essentially the hydrogen, and how the hydrogen is formed. That will be the sharing of the 1s electrons. You're going to have the 1s from one hydrogen and the other 1s from the other hydrogen. You have overlapping. So this is actually called, remember that, and SS sigma bond. It's head-to-head. And this one is head-to-head. And then we're looking into the chlorine, and you will see that will be the overlapping. So this is a 3p orbital from chlorine, this is a 3p orbital from the other chlorine atom. So this one will be pp sigma bond. Okay, there will be the pp sigma bond. Then we'll see looking at the oxygen, and this is the correct Lewis structure for oxygen. And you were looking at the oxygen, you will have the 2s, two electrons, 2p, actually have 4, 1, 2, 3, 4. And one of this is going to form 2p hybridized orbitals. Not hybridized orbitals, the sigma overlapping. So this one is a 3p, and not a one. I'm sorry. This one will be 2p, and the other one is from the 2p from the other oxygen atom. But when you are realizing when that's formed, there's another lob of the p orbitals and the half. Each has a single electron on it, so this is actually overlapping. And now we have a pi bond. Okay, so we have lots of sigma bonds, we have lots of pi bonds. It's characteristic for sigma and pi So sigma versus pi bond. Sigma bond can rotate, while pi can't. The reason is very simple. If you know the sigma, the sigma bonds, it's a head-to-head overlap, so they can actually rotate those two atoms that is forming this bond freely. Okay, so those are the characteristics of sigma bond. But when you're looking at the details about how the pi bonds are formed, this is for the overlapping of perfectly aligned p orbitals. Okay, so then p cannot. Sigma bond are stronger. Okay, so then the process of trying to figure it out is connect the atoms with sigma bond first, then looking for pi bonds, pi bond O bonds, and that requires perfect aligned either p or d orbital that will be participate in the bonding. As we said before, now take a look at an example. Will be methane, CH4. If you write the Lewis structure, it will be CHH. Each one of them will be connected with a single bar. Each one of them is composed of a pair of valence electrons. A pair of valence electrons shared between those 4 hydrogen atoms and carbon atom. And now you're looking at how actually those bonds are formed. So then this is going to use valence bond theory. Now you start looking at for H, for this electron it's easy. So it's on the 1s orbital that will have that. Now we're looking at carbon, and carbon, the valence shell orbital notation will have 2s and a 2p. Oops. And 2p. So total valence electrons for carbon is 4. You will first go to the pair here. The other one has to spread out like this. Spread out like this. And now we're looking at as the ground state. Carbon only has 2 legible p orbitals that can form bonds with hydrogen. And don't forget, all those p orbitals, they are all perpendicular to each other. As you can see, if I use this, really indicating the knob is going to the front, Those are the 3 p orbitals. They are mutually perpendicular to each other. But now you have only 2 of the 2 p orbitals that are legible for forming bonds, and the bond angle between those would have been 90 degrees. But now clearly indicated on the Lewis structure, you should have 4 connections on the central carbon atom. So how the carbon is going to resolve that, introducing the concept of hybridization. So it's 2p, and so this is essentially what we're looking at, how the nature is going to handle this dilemma. You need 4, but you only have 2 that is qualified to be able to form a sigma bond with the surrounding hydrogen. So what nature does, it actually takes all the atomic orbitals, in this case for valence electrons for carbon, they're actually going to make 4 equivalent hybridized orbitals. So this is 1s3p, 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 1s3p. So those generating 4 sp3 hybridized orbitals. So it's generating 4 hybridized orbitals. So in this case now actually I can use the Hund's rule to put 4 valence electrons on those 4 sp3 hybridized orbitals, one on each. So this is actually preparing those orbitals to be bonded with 4 hydrogen atomic orbitals, and that will be the1s orbital for hydrogen. So they actually can form covalent bond now. So this is actually comes out, the hybridization comes out of the necessity. And here comes the concepts. And the things stemming from central atom do not provide sufficient number of orbitals with a single electron for proper bonding with surrounding atoms. And this is the way you're looking at it, the previous question, and that will demonstrate that. In that case, the carbon will not have enough. Orbitals, atomic orbitals to form 4 connections. So this is where it's coming. The hybridization of atomic orbitals is coming out of the necessity, and also with the proper orientation in 3-dimensional space, and provides a viable solution. And when you're mixing those orbitals together, you pay a slight energy penalty, but for the bonds to be formed, is going to make the compound much more stable. So the mixing of several atomic orbitals to form the same number of hybrid orbitals. I emphasize same number. Okay, so if you are mixing with 2 atomic orbitals, you should have two hybridized orbitals, called hybrid orbitals. All the hybrid orbitals are formed are same in the shape and energy, but different in orientation in 3-dimensional space. And as you can see clearly very quickly. So the first thing I will want to address is this coming out of necessity to collect 4 hydrogen atoms to the central carbon atom in methane molecule. So this actually gets sp3 hybridization. The sp3 hybridization, you take just as the diagram illustrated for the molecule CH4 in the central atom, the carbon has to form 4 bonds. To reconcile that, we're actually mixing 1s orbital and 3 p orbitals to give you 4 individual hybridized sp3 orbitals, so they can get them ready to get bonded to the surrounding atoms. As you can see, let's recall for a little bit unit 3 when we talk about electron configurations. This is going to be the atomic orbitals for 1s. This is 1s orbital, and now we get to 1s, 2s. You have those general shape, but just in between this is you have they have the 0 regions. And now the P's have the dumbbell shape. This is on the y-axis, this is on the x-axis, this is on the z-axis. They are all mutually perpendicular to each other. And when we mix it together, remember, those lobes would have positive and negative sign associated with. So for the S, they're always positive, so there will be positive and negative, and positive, negative. When you carefully mixing those 4 atomic orbitals together, you will have 4 hybridized orbitals. For those dealing with the plus-plus interaction, you're going to have a big blob. You have a much smaller block because now you can start combining positives with the negatives. Positives with negatives. And also interesting, you can carry out all those operations. You will have the geometry of that, and it seems all the high density, so high probability of finding a particular electron is now moving. It's on the axis. So this is another way of illustrating the sp3 hybridization. You have the s orbital, now you have p orbitals. Those are 3 p orbitals. Remember, you should be drawing them to be perpendicular to each other. So you will have 4 sp3 hybridizations. So those numbers is indicating how many of this particular orbital. In this case, sp3, you have 1 s, 3 p's, total 4. And here is another couple of good illustration about the sp3 hybridization. The difficult part is now we're dealing with a 3-dimensional shape. This is a perfect tetrahedron. So those angles are pushed out, and this is the one with a single electron on those 3p orbitals. Actually, in this case, it's 2p. It's 2p atomic. The hybridized atomic orbitals. When they mix together, they form hybridized orbitals. Then those 4 hybridized orbitals are perfectly tetrahedral, pointing towards the corner, used for hydrogen. Here's another illustration about the geometry. When you have sp3 hybridized central atom, and then you have then you're going to have a tetrahedral geometry. So in this case, we kind of summarize when the electron group is 4, and this one is the molecular geometry can occupy up to tetrahedral geometry. And in this case, it's combined 1 s orbital and 3 p orbitals. You end up with 4 sp3 hybridized orbitals, and it has a tetrahedral geometry. Okay, as shown here is the angle between the lobes, and it will be 109.5 degrees. And this one is very important to the tetrahedral shape, and every molecule with a total of 4 atoms and lone pair is sp3 hybridized, and give us trigonal pyramidal and bend shapes. This one gives the sp3 geometry. So now let's take a look at NH3, the ammonia, a couple of issues we'd like to address. Ammonia, okay, so in this one, take a look at the nitrogen, the central atom, nitrogen. You have 2s, you have 2p, you have 3 orbitals, and that would be the orbital notation for nitrogen. As you can see here, I already have have 3 p orbitals, each one with a single electron. That's really to get paired. And then you say, why not? This is the 2p is going to pair with the 2p going to pair with the hydrogens. However, for that particular combination, then those, don't forget, those 2p orbitals are actually perpendicular to each other. So then the molecular shape will just be H, H, and H. Each bond angle will be 90 degrees. And that's a little bit too tight. How we can actually utilize this vast space to relieve the strain imposed by this pretty sharp 90-degree bond angles. So in this case, if we actually take those and make it 4 sp3 hybridized orbitals, now and we have a pair. So now those hybridized sp3 orbitals really to be bonded with the 1s orbital for nitrogen. For hydrogen. And this is actually going to give you a trigonal planar. It's a trigonal planar geometry, and it gives you the ones for the sp3. They all pointing towards the central atom. And now you can see the other apex to the tetrahedral is occupied by the lone pair. So in this case, and also the bond angle now here will be 107.8. This situation is a lot better than the 90-degree bond angle. So in this case, nature actually choose the sp3 hybridization. Choose the sp3 hybridization to give you a tetrahedral, and then you have the trigonal pyramid shape for the molecule, and that gives you the central atom, nitrogen, will have a sp3 hybridization. One of the sp3 hybridized orbital will contain a lone pair. So then let's take a look at another one of importance. That will be water. Okay, that will be the water as a pair, as a second pair. Overall, is still a tetrahedral shape because of the electron groups, and the shape it will be bent based on Vespa. So now actually looking for the valence bond theory, take a closer look at oxygen. Okay, so the oxygen, the atomic orbital notation for the valence electrons. So it will be 2s and 2p, 3 equivalent orbitals, and you should have 6, right? 1, 2, 3. Okay. Oops. That is the reason why. Gotta be careful. Gotta set it up. Okay. So they have two. They have the two 2p orbitals. That is really actually to be be bonded with the other surrounding atoms, the atomic orbitals. And in this case, and you can see they do have two. They can directly link with overlapping. They can directly overlap with the hydrogen 1s orbitals. However, if that is the case, remember this p orbital is perpendicular to that p orbital. We again will have molecular geometry, molecular shape of 90 degrees. It's too much strain. Okay, so this is too much strain. So nature have a better way of handling that. That would be you get all this, mix them up, and then you have 4 sp3 hybridized orbitals. Then you have 2 of them filled with paired of electrons and 2 singlets here. Now it is ready to be bonded with the hydrogen 1s orbital. That will be this one, that will be that one. Actually, now we have H, O, and H now. Because of 4 electron groups, sp3 hybridization, then you have to obey the tetrahedral. The tetrahedral, you have 2 lone pairs on the oxygen that will push this 2 down. And remember, the bond angle is going to be smaller than 109.5 degrees, which is associated with perfect tetrahedral. And in this case, it's 104.5 degrees. And in previous unit, you learned why this is deviating, because of the lone pairs are larger. It's less constrained, only interact with one nucleus, compared to the bonded valence electrons. They have to interact with 2. So given that, for the NH3 and H2O, they all utilize the hybridization to get to the optimum geometry. And as you can see, 90 degree is more strain as compared to the 104.5. So then now let's take a look at another class of molecules that require a slightly different approach in terms of hybridization. And let's take a look at, let me change the color back to the one that's white, BF3, and this one is boron trifluoride, and you can write the Lewis structure out. Oops, and this is wrong. That should be the F. Okay, and this is all starting with the Lewis structure, the trigonoplanar electron group geometry, and then trigonoplanar molecular geometry. So how about we're looking at from valence bond theory perspective. So now if you're looking at boron will have the 2s, we'll have the 2p, and let's draw it slightly differently this time around. Okay, 2p will be separate, and for boron you have 1s2 2p1. You have 1s2 2p1. And how I'm going to actually, you notice the boron is going to have 3 connections, and you only have 1 2p orbital that's ready for bonding. So you need 2 more. How you're going to get 2 more is going to becoming crucial. As you can see, and this is going to take 2 2p orbitals. One is half full, the other one is not filled at all, and the 2s, you can view the 1 2 3. Remember how many of the atomic orbital you take, you will have mix them together, you will have the same number of hybridized orbitals. In this case, I have sp2 hybridization, and given that, you'll have this arrangement, and now the sp2 will have the connection with the fluorine, and then you can have you can have sp2p 2p overlap, gives you the proper sigma bond between the boron and the fluorine. Okay, boron and the fluorine. Again, this is coming out of necessity. We cannot just use the atomic orbital of boron and use to be bound with the 3 fluorine atoms. So this is a kind of a new kind of hybridization. This is what we're going to discuss, and this is called sp2 hybridization. It's a combination of 1s atomic orbital and 2p atomic orbitals to give you this hybridization with proper 3-dimensional geometry. So as you can see here, now we take this is the s, and this is one of the p, this is another of the p orbitals. Notice they will have different directions. This one's on the y-axis, this one's are surrounding the x-axis. So when we mix these two, remember when the Schrodinger did the model, he comes up with the positive and negative, positive and negative. This is just purely mathematical calculation for electron considerations. Has nothing, I emphasize to say it again, have nothing to do with charge of an atom or with the charge on those ions. Okay, so if you start mixing those and start flipping those plus and minus signs, you will have 3. Those are the 3 hybridized orbitals, and now you can see them as illustrated here, and you have 1s orbital mixed with 2 2p orbitals and form these 3 sp2 hybridized orbitals, but you have an empty p orbital. It's right perpendicular to all the 3, and this is the empty p orbital. But now from the top view, you will see those 3 lobes again forms a perfect trigonoplanar. The angle between those two will be 120 degree. Okay, so those are the examples. It will be the BF3 boron trifluoride, C2H4. We're going to discuss later. This is called methane, and this is aluminum chloride. And you will have the one, the geometry is 120 degree between its trigonoplanar. And then you're wondering, for us to write C2H4, the proper Lewis structure will be this. And now you're looking at the double bond. Okay, and where is this double bond? So far we have not discussed about it, and in this case it's for the formation of the sp2 hybridization, and that's dictated by necessity. And now you have this 3 sp2 hybridized orbital, and now you have a p orbital that is located here. It's one on the top, one on the bottom, one on the top, one on the bottom. And as you can see, if we start linking this hybridized orbital with the hydrogen, in this case, with the hydrogen. This will be the 1s for the outside hydrogen. Okay, for the outside hydrogen. The unoccupied p orbital that is perpendicular, straight, going through this paper. Okay, so you form a sigma bond first. There will be the sp2 overlap, and now you can actually have the 1s sp2, 1s sp2, and 4 of them linked with the hybridized sp2 hybridized orbitals. Okay, and you can actually calculate the bonding angle between those. So it should be 120. And now you start looking at, that situation is quite similar. It's quite similar to the oxygen. Now with the proper orientation, you form the sigma bond by the sp2 overlap, and also sigma bond by sp2s overlap. Now you're actually looking at this p, these 2p orbitals are perpendicular to the plane, and they now can have the chance to overlap the plus knob with the plus knob, the negative knob with the negative knob. This is the formation of the pi bond. Okay, so that explains the C2H4. The bonding is explained by valence bonds theory. And again, you're looking at, now this is the ethene, or sometimes referred to as ethylene. There's a double bond here and single bond between the carbon and the hydrogen. Now you understand those are the single bonds. Those are the hydrogen bonding with the hybridized orbital on the carbon atom. So the same thing, they form a sigma bond first, then now you're looking at it, it's the possibility of overlapping between the two lobes of the perpendicular P. So that requires them to line up perfectly. So this is also, say, the visualization of sp2 hybridization in ethane, and now you'll have this carbon hydrogen, length of it is 1.08 angstrom, and now you have this double bond. It actually has a 1.33 angstrom, and you have all those angles. You can see ball and stick model, and you can also see space filling model, or you can see the electrostatic potential map for ethylene. This is essentially to calculate the density of the electron groups, of the orbitals and how they are organized. So then this is sp2 hybridization in ethylene, C2H4. So each one of the carbon will assume a trigonoplanar shape, and between those it will be 120-degree bonding angle. And now you'll understand with the double bonds, you always have one sigma bond and one pi bond. Okay, one sigma bond and one pi bond. Sigma bond is formed first, then the 2p that's not participating in that will have the proper orientation to have the proper overlap and have a shared pair of valence electrons. Okay. So now we're looking at another example. This one will be beryllium chloride. Okay, so you're going to go beryllium is another exception. It will be quite deficient in terms of valence electrons. But this is going to be linear shape, molecular shape will be linear, and it's 180 degree in the bond angle. So now we know the chlorine will have 2p orbitals ready to go with 1 electron on it, and the other one will also be quite similar, got a 1 electron on that, and that will be the 2p from chlorine. Okay, so it's chlorine 1, chlorine 2. Now we are looking at beryllium, and by itself you have 2s, now you have 2p, 2s, 2p. Now you can see I only have 2s2, and this is trouble because this is paired. I cannot use this to be bonded with the surrounding atom. And how am I going to do that? Going to take those two, and you're going to have what we call it sp hybridization. Sp hybridization. Each one will have electron spinning in certain ways, ready to get bonded. We're ready to get bonded. So now when you mix, this is what we call the sp hybridization. Now let's take a look at the detail about it. You take one s orbital and one p orbital. This is what you're going to get. And when you add them up, because of the sign for the electron density for all the other structures like trigonoplanar, tetrahedral, trigonobipyramid, and trigonobipyramid, and octahedral. So all those will have plus lobs and negative lobs. Reminder again, those are not full charges. So now you end up with all the s orbitals. They all have a single positive number associated with it. So when you add s together, so the positive sign, the lob, start to increase, and same token, the negative sign orbital, p orbitals, starts to shrink. So the s orbital adds to the lobe of the p potential, and this s orbital subtracts from the lobe of the p potential. So then this one's add, the other ones cancel. So that's why you can have this shape of hybridized. This in this case sp hybridized orbitals. So in this case, now we have this, and now they are oriented 180 degree apart. And now you can see right here, and that will be the angle will be 180 degree. Okay, it will be 180 degree. So then what's about the sp? It takes one s and one p to hybridize. The shape of it, the hybridized orbital, is linear. Case in point. And sorry, this one should be C2H2. It's acetylene. Okay, this one will be the acetylene example. Okay, now take a look at sp hybridization. You can have hybridized molecules is 180 degree in between, and now you only have now the other two p orbitals will have the potential if we provide with the right angles, and then they will form a pi bond. Okay, so in this case, now I have this one. I have the mirror image of this for the other molecule. So then they will come in, and for the other atom, so they will come in from a single bond first. But now you have those two that are perpendicular to each other, and if the orientation for the other part is perfect, aligned, they actually could form a pi bond. So as you can see, this is a pi bond, and also like that flat, that is also a pi bond. And also when we later on learn the triple bond double bond are possible. So when we have the sp hybridization, and this one is a sigma bond first, and then now you have those two pairs of the two p orbitals. They are aligned perfectly. They're parallel. They're aligned perfectly, and then gave you this. This is one sigma bond, two pi bonds. Okay. So this is the one actually has the sp hybridization, and is indicated here. Now you have the sigma bond. Now you have two pi bonds. One is on the top, the other one is on the side. Top bottom is on the left side to the right side. So for molecules like PCl5, and now you start looking at, wait a second. Now the P has to provide connections more than 4. How are we going to accomplish that? Remember, phosphorus is the group 3. It's the period 3 elements, and remember, period 3 elements will have the d orbitals available for them. So in this case, and you can have the opportunity to couple with more valence electrons. So in this case, if I need 5, that would be the sp3d hybridization. Proper calculation, you will have the shape coming back again. So this is a trigonal bipyramid. Okay, as you can see here, it's the other one. This is the 5. You can have the sp3d, and you notice here 1 plus 3 plus 1 is 5. Now how about we have 6? So the next logical step will obviously go to the sp3d2. When those starts to hybridize, you will have an octahedral shape. You're going to have the octahedral shape. This is the side view, and it's perfectly square here with a kind of a dumbbell running through it, and this one gives you the top view. Alright, so then we learned in the valence bond theory, in looking into the details about how those bonds are formed, and always hybridization comes out from the necessity. Generally, they have to form the sigma bond first to connect those atoms together, surrounding atoms and the central atom. And now we can actually use the hybridization to predict the geometry of the electron pairs. So in this case, as number of lone pairs plus number of bonded atoms, this is essentially number of electron groups. Okay, and hybridization will be sp, and examples with beryllium chloride. And now number of bonded atoms, we move it up to 3. Hybridization will be the sp2. We have all these explanations with the examples. Now you should be really understanding it very well. So in this case, it's boron trifluoride. If you have 4, you can have sp3, and you can have all kinds of molecules that will have the number of electron groups equal to 4. The shape of that will be a tetrahedral. So you have all the methane, that will be a perfect tetrahedral. This is kind of start getting deviating from the perfect tetrahedral by putting a lone pair on the nitrogen atom. H2O also it's the same argument. Now you have all this trigonal pyramid, and this is the bent. Okay, so now I have 5 electron groups that are including the lone pairs and the bonded valence electrons, and this is called sp3d. Now you gotta have the d orbitals involved because it goes beyond the s, and the p can accommodate. S can accommodate maximum 2 electrons. P can accommodate up to 6. And in this case, it's a PCl5. Okay, 6 will be the sp3d2, and you will see the SF6. Well, running down here is the hybridization of the central atom, gives the molecule its ability to bond properly. So if you have 2 electron groups, it's sp, it's linear. 3, sp2, that will be trigonoplanar. 4, that will be sp3, that will be tetrahedral. 5 is sp3d, that will be trigonobipyramid. And 6 will be sp3d2. sp3d2. So with that, that's this slide summarize that. You'll have sp3, it will be the tetrahedral for electrons. sp2, that will be trigonoplanar. sp, that will be linear. sp3d, trigonobipyramid. sp3d2, that's octahedral. And now you can see it's converging back to the shapes predicted by the Vespa theory. So the geometry of molecules, any molecules, will be determined by the number of shared and unshared electrons. Okay? As you can see, here is another way of summarizing what you just learned. sp3 hybridized orbitals. You take 1s, 3p, and now you have 4 sp3 orbitals, and then that list goes out. Okay, so with that, that's the conclusion of the podcast on the valence bond theory, and please review this podcast if it's necessary, and also complete the worksheet on the valence bond theory, essentially looking at details, how those bonds are bonded together. Turns out if you have a double bond, they're actually not equivalent. 1 sigma 1 pi. If you have a triple bond, 1 sigma 2 pi. Thank you very much for your attention.